Let's get into chapter 17. This is a good chapter. We're not going to be able to finish this chapter before we break for lunch, but excellent chapter in discussing the nature of our dynamic routing protocols. We're not going to get into the specifics of each protocol as of yet, but we are going to start to learn more and more about these dynamic protocols. Dynamic routing protocols have been around since the late 1980s. The very first dynamic routing protocol was the Exterior Gateway Protocol, which was developed in 1982. Wasn't a very good routing protocol, but it did certainly meet the requirements at the time. IGRP, which was a Cisco protocol, was the very first protocol that was used internally, inside of your network. It was developed in 1985. RIP, actually, most people think that RIP was the first routing protocol, but RIP was actually designed as an open standard version of IGRP. The problem with IGRP was that it ran solely on Cisco routers. So RIP version 1 came out, and you're going to see there are a lot of similarities between those two protocols. RIP version 1 came out in 1988. What's common between these three protocols? We don't use them anymore. All right? Here's the primary reason. All three of those protocols are classful. What does it mean to say that these routing protocols are classful? They don't do subnetting. They don't support subnetting. Not good. All right? In 1990, ISIS came out, and then OSPF, and then EIGRP, RIP version 2, BGP, you get the idea. But everything beyond this boundary was classless. Of course, all of our IPv6 protocols are classless because we never had classes defined. So these are what we kind of consider to be our modern routing protocols. The most widely used routing protocol is OSPF. Not because it's the best, although most people would argue that OSPF is one of the better routing protocols, because it was open standard. EIGRP at the time was still Cisco proprietary, meaning that you had to have Cisco devices to be able to run it. EIGRP also has its roots tied into these legacy protocols. But there are a lot of enhancements that were made to EIGRP to make it act more like a modern routing protocol. Now you also notice that we have different classifications for our protocols. We have a box over here that represents what we call exterior gateway protocols, and we have a box over here that represents what we call interior gateway routing protocols. Exterior gateway routing protocols are routing protocols that you would run on the internet, between organizations, between companies, etc. Whereas interior routing protocols are protocols that we would run inside of our enterprise. These are protocols that we're going to run inside of our enterprise. All right? Things like EIGRP, OSPF, ISIS, and so on. Because these are designed to function in different types of environments, these exterior protocols are much, much different than our interior protocols. And really, there's only one exterior protocol. EGP doesn't exist anymore. So BGP is really the only exterior protocol that we have. The other thing that you'll notice is there's kind of a subclassification of these protocols. Distance vector versus link state versus path vector. Path vector protocols don't use metrics. They use these things called path attributes to make routing decisions. We'll get into that when we get into the BGP discussion later on. Hopefully we get to BGP when we get towards the end of the day here, but We'll see, right? Depends how long it takes us to get through the rest of this stuff. I'm going to teach you guys what the fundamental difference is between link state and distance vector. There is a huge difference between those types of protocols. Link state and distance vector directly relates to how the protocols see the network, the algorithms that they use, and the way that they visualize the actual network. All right? I won't do it right now, but there is, well, distance vector traditionally has been kind of considered to be subpar to link state. Link state generally is considered to be more knowledgeable, but not necessarily. It depends, right? For the most part, it's true, but EIGRP kind of gets classified in this group over here. It's kind of like if you're on a singing competition and you watched all the auditions and you saw these three people that really sucked, you wouldn't want to be in their group when the voting was taking place, right? Especially if they were eliminating people, because you put in that group means that you sucked just as bad as they did, right? Well, that's not the case here. EIGRP does kind of stand alone, all right? What is the purpose of a dynamic routing protocol? What is the purpose of a dynamic routing protocol? To allow routers to automatically exchange routing information, right? To be able to tell when new networks show up, to be able to update metric information and reachability information for those destinations, to be able to calculate what the best path is for a particular destination. And if that best path doesn't exist anymore, using an alternate path or finding some sort of different way of routing to that destination. In order for all of this to happen, these routing protocols have to build databases. They have to exchange messages. They have to run calculations. And this is really one of the important slides of this particular section. One of the very important slides of this particular section. We have these things called data structures. You can think of data structures as databases, where all of the information that I'm learning is kept. Now, you guys are already aware of one data structure that exists. It's called the routing table. But we also know that the routing table is the last thing that we figure out, because what goes into the routing table? My best routes. Before I can put everything into, bless you, before I can put everything into my routing table, I have to figure out what those best routes are. We're going to learn specifically what kinds of data structures are built with each protocol, but think of data structures as just databases that contain information for that routing protocol to function. We also have routing protocol messages, hello packets for routers to be able to identify each other, updates for routers to be able to exchange routing information, queries for routers to be able to ask for routing information, and so on. The language that the routers speak in order to actually build the databases. The messages allow us to construct the databases. And then lastly, the logic, the algorithm. EIGRP has a particular algorithm that it uses to make decisions. OSPF has an algorithm that it uses to make decisions. These three components are common to RIP, to OSPF, to EIGRP, to ISIS, to BGP. Very, very important concepts when it comes to determining how these protocols work. We're going to do a deep dive in each of these three components for each protocol that we discuss. All right? So what are the advantages of having a dynamic routing protocol? Of course, we get to automatically share routing information as necessary. we can figure out what the best path is on the fly. And if that best path fails, we can use a different path. In static routing, that would require you to go in and change the routes manually. The disadvantages, all of this automatic calculations, all of this sharing of information, all the communication between the routers requires overhead. Not to mention, you have to understand how these protocols work. It's a language. And if you don't understand how to implement this architecture appropriately, you can actually cause a lot of problems in your network. You can open up a lot of security vulnerabilities, for one, absolutely, and you can also have invalid routing information, suboptimal routing, asymmetric routing. There's a lot of things that can happen if you don't implement your routing architectures correctly. All right? So how does a dynamic process work? Well, it's pretty simple. We send and receive messages on the interfaces that have the protocol enabled. All right? Those messages can be things like hellos, hey, I'm out here, I'm an EIGRP router, I'm ready to talk to you. Or it can be routing updates, or it can be when metrics change, whatever. We share these information to all the other routers that are talking the same language. This is how we learn about remote networks. This is how we learn about how to reach remote networks and so on. If the topology changes, we can recover automatically. What is the process of that recovery called? Convergence, right? It's called convergence. You guys agree? Okay. The faster that a protocol converges, the more efficient it is. Some routing protocols converge more quickly than others. The rest in peace routing protocol doesn't converge very quickly at all. Right? RIP. All right? Whereas EIGRP and OSPF are very quick to converge. But even the convergence time that takes place is dependent upon how you designed the protocol itself, how you implemented the protocol itself. So not only am I going to teach you about the fundamentals of these protocols, but I'm going to teach you about the best methodologies for implementing these protocols. A network is said to be converged when all routers have completed their calculations and they all have accurate information about the entire network. Older protocols like RIP, very slow to converge, whereas the newer protocols like EIGRP, OSPF converge more quickly. Think about it. If a topology changes, it's going to affect the data passing through the network. If it takes 60 seconds to converge, that's pretty significant. We're talking about convergence times in the millisecond time frame. All right? So here is a flow chart that kind of represents that architecture that we talked about on the first slide. Dynamic protocols have two general categories, interior, exterior. My exterior routing protocols use a path vector algorithm, and the only one that falls under this category today is BGP, the Border Gateway Protocol. My interior protocols have two subclassifications, link state and distance vector. OSPF and ISIS are considered to be link state routing protocols. All the other ones are distance vector. And again, EIGRP kind of stuck in that group. But EIGRP gets the wild card vote, so it can continue singing because it has enhancements, which is why it's called an advanced distance vector protocol. It has enhancements in it that allows it to act very much like a link state protocol. I have to say, though, fundamentally, at its core, it's still distance vector. At its core, it is still distance vector. All right? Like I said, I'm going to explain the difference between link state and distance vector to you guys in the next couple of slides. Actually, I might do it right after lunch. All right? So RIP is a traditional distance vector routing protocol. RIP version 1, not so great, very, very bad, primarily because it's classful, doesn't do subnetting, but it also doesn't scale well. It does periodic updates. What does it mean for a routing protocol to do periodic updates? It sends out updates every X number of seconds. In this case, 60 seconds. When should a routing protocol send out updates? When something is changed, exactly. Why do I need to send you the same information over and over and over again when nothing has changed? That would be like a wife, right? Telling you to do something over and over and over again, right? If nothing has changed, why would I need to send you additional information? We like to have our routing protocols act incrementally, meaning that they send out updates when there are changes. IGRP and RIP both are periodic protocols. They both send out updates when a certain amount of time expires. In RIP, it's 60 seconds, and IGRP, it was 90 seconds. EIGRP does incremental updates. It sends out updates when something changes. All right? By the way, these protocols here also, not only are they sending out updates every X number of seconds, they're sending out their entire database. Well, when I'm sending out an update, what should I actually have to send? Only what changed. All right, which is called a bounded update or a specific update. EIGRP seems the one to go if someone wants to use distance vector. Well, yes, absolutely. If you're going to use distance vector, that's the only choice. First of all, IGRP doesn't exist anymore. RIP version 1 is classful. RIP version 2 is classless, great, but its metric is hop count. A metric of hop count, not so great, right? All right, distance vector still does get kind of a bad rap. So let's talk about this. This will be the last thing we'll talk about before we break, because there's a lot more slides in this particular chapter, but I don't want to rush through them for the sake of being done here before lunchtime. But distance vector versus link state. This is a very difficult concept for some people to comprehend, so I'm hoping this discussion will help you in that understanding. Let's talk about this from the perspective of router 1. In both cases, router 1 is trying to reach this 10 network. All right? Now on the top, we have our distance vector protocol. On the bottom, we have our link state protocol. When it's all said and done, regardless of whether it's distance vector or link state, what is the goal of R1 as far as reaching these networks? What router do I send the packet to next? So I want to make it clear that regardless of whether it's distance vector or link state, that decision is still the same. Routing is always about sending the packet to the next router. It's how I determine that next router is what the difference is between these two protocols. So let's say router 6 here, which we know is directly connected to the 10 network, advertises the 10 network to its neighbors. Okay? Router 6 advertises the 10 networks to its neighbors. And on top of that, it advertises that network with a metric. Simple enough. Router 6 says, hey, I have the 10 network. And by the way, if you want to get to the 10 network, this is what it's going to cost you. So router 4 knows about the 10 network. But router 4 also learned about the 10 network from router 5. because they're all neighbors. Router 4 talks to router 5, router 4 talks to router 6, etc. Now, router 4 has to make a decision. Do I go this way to get to network 10, or do I go that way to get to network 10? We know how that decision is going to be made. It's going to be made based on a metric. So router 4 makes its decision. I'll just put an exclamation point here. I got my route. Router 4 then advertises its choice to router 2. It doesn't advertise that it has 2 ways to get to the network. It just advertises the route that it chose. Does that make sense? So by the time I get to router 2 and router 3, router 2 has a couple of choices. Router 3 has different choices. But by the time I get to router 2 and router 3, router 2 advertises the path it chose. Router 3 advertises the path it chose. So essentially, from router 1's perspective, it has to make its decision on how to get to the 10 network solely based on the information that router 2 and router 3 provided. Not only that, router 1 has no visibility of what this network actually looks like because it didn't know about these other links that were in the path. It's simply choosing to get to the 10 network based on router 2's choice and router 3's choice. There's a term we use to describe this. It's called routing by rumor. Routing by rumor. So you might look at that and go, well, yeah, but if all the routers make the right choice, we should be choosing the best path. And that's true. If all the routers make the right choice, we should be choosing the best path. But there's no control here. Router 4, you could have a policy in router 4 that says if this path is mathematically the best path, but you could put a policy in router 4 that says to choose this path. That would be the path that would be advertised to router 2. So router 1 is really at the mercy of the other routers in the network to decide which direction to go. Now, router 1 might choose to go to router 3, and that might actually be the best path. The bottom line here is, as a distance vector protocol, I only make my routing decisions based on 2 things: what direction, vector, and how far, distance. Distance, vector. What direction do I go and how far is it? I have no idea what's included in between, but I do have an idea of how far it is, and I do have a general idea of what direction I need to go in. Distance, vector. Link state, on the other hand, is very interesting, because in link state routing protocols, R6 doesn't only advertise the 10 network, R6 advertises every single network it's attached to, all the metrics that it's attached to, and sends that information over to router 4. That information goes into something called an LSDB, a link state database. R4 conversely collects all that information from all the routers. When it sends its advertisements to router 2, not only is it advertising the 10 network, it's advertising this network, and this network, and this network, any network it's attached to. Sorry, not that one down there. Well, it would advertise the one between 5 and 6 if it was learned through 5 or 6. The bottom line is, by the time I get to router 1 is not only aware of the 10 network, it's aware of this network, this network, this network, this network, this network, and this network. Who they're connected to, what their metrics are, and so router 1, when it wants to make a decision on which way to route, it tests all of those paths. It looks at the values for every path, and it makes its routing decision based on knowledge of the entire topology. That's why people generally classify link state protocols as more understanding, or at least a little bit more knowledgeable. But on the flip side, you can imagine that the databases are much more complex, and the information that has to be exchanged is much more detailed.
And the database has to be bigger.
The database is larger, yes. Why is it called link state? Because router 1 knows the state of every link in the topology. Now, ultimately, and I have to make this clear, I say that a lot, but I need to make a lot of things clear. Ultimately, whether or not I know the whole path or I don't know the whole path, the routing decision is still to the next hop. Every routing protocol makes a decision on how to route based on the next hop. Where do I send the packet to next? That doesn't change. Okay? So, unfortunately, with EIGRP, we have to have mechanisms in place to handle things like loops and convergence and whatnot, because these distance vector protocols, they don't have as much visibility as the link state routing protocols do. Here's the analogy, and this is the final thing that we'll do before we take our break. The analogy is this. A distance vector routing protocol is kind of like following road signs along the road, right? You're driving down the highway, right? What do you see? You see a road sign that says Los Angeles, and it says 159 miles. Okay? Well, you know it's that direction, you know it's that distance, but you know what is included in that 159 miles? No. And as you drive down the road, there's a turnoff on the highway, and there's a sign that says Los Angeles that way, 67 miles. So you're still getting to the right destination, but you're waiting for those road markers along the way. Whereas with link state, you have the whole map, like a GPS. Or if you're old school, the little fold-out maps that you used to have, right? Thomas Guide, yeah. Okay? So hopefully that gives you guys a better understanding of the fundamental differences between link state and distance vector. As you can see, it's pretty significant. All right? We'll go ahead and pause right now. All right, so that is the primary difference between distance vector and link state, as we had talked about, well, before our lunch break here. All right? Sorry about that. I unmuted everybody. All right. Now, distance vector, as we talked about before the break, distance vector routing protocols, well, they're designed to share routing information between their neighbors. We're going to learn about this concept of neighbor relationships as we kind of move through the rest of the chapters here. But being neighbors means that we're sharing information with those neighbors. We talked about the concept of we're not aware of the entire network topology. We do this thing called routing by rumor. All right? Remember what routing by rumor was? Anybody? The concept of making routing decisions based on what my neighbor's decision was. Not based on my own choice, but making my routing choice based on what my neighbor's choice was. Some of these distance vector routing protocols send periodic updates. RIP version 1, IGRP, they send periodic updates. What's up?
I want to know about the ASA, if we can work on that today. After.
Yeah, I talked to Tim.
Okay.
Yeah. Okay. Now, even worse than that, some protocols like RIP version 1 and IGRP, not only do they send out periodic updates, we talked about that concept of sending periodic updates is not necessary, but they send their periodic updates to a broadcast address. 255, 255, 255, 255. Even if the topology is not changed, we're sending out these updates every X number of seconds. Now, routers, by design, are really supposed to stop broadcasts. But unfortunately, these older routing protocols actually create these broadcasts. Now, that means that we're consuming bandwidth, we're consuming network resources, even though we don't have to. Really, it's not very efficient. Now, RIP version 2 and EIGRP switched from using broadcast packets to disseminate routing information to using multicast, which is good. Multicast means that only the devices that need to see that information, in other words, the devices participating in that particular multicast group, are going to actually use that information. But even further, EIGRP only sends out updates when the topology changes. They only send out updates when there are changes in the network. So remember I said when we started to talk about these routing protocols that EIGRP is more of an advanced distance vector protocol. It's for this reason. EIGRP tends to do things a little bit more like a link state routing protocol. The concept of classful versus classless. We already know this, right? A classful routing protocol is one of those protocols that does not support subnetting. In other words, it assumes when it's sending routing updates or receiving routing updates, it assumes classful network masks. All right, RIP version 1, IGRP, these are both classful routing protocols. They can't do things like variable length subnet masking. They can't do subnetting. They also have problems when you have discontiguous subnets because they make the assumption that if I get a 10.10.10.0/24 network advertised, well, first of all, I would never see that. But if I did see something like that, then I would just assume it's 10.0.0.0/8. All right? Classless routing protocols, which are all of our modern routing protocols, they're going to support subnetting. They're going to do VLSM, they're going to do classless interdomain routing, etc. Anyway, let's talk about that term, by the way. I mentioned it, CIDR. Anybody that kind of deals with CCNA level material, they're going to be introduced to this concept of CIDR. CIDR stands for classless interdomain routing. Essentially what it means is that the routing protocol not only sends out network information when it's trying to reach a destination, but it also sends out subnet mask information. All right? Subnet mask information. Now, having the subnet mask information is important because now I can identify the individual subnets. All right? So here's a chart that really kind of identifies the pluses and minuses of each of these protocols. As you can see, my legacy protocols, their convergence time, pretty slow, right? Slow, 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 whereas our link state and even EIGRP, very, very fast to converge. Scalability, small. What does scalability mean? How many destinations can I support? How many routes can I support? What is the density of the network? And so on. The legacy protocols, those tend to work very well in much smaller environments. As you can see, OSPF, ISIS, those scale to very, very large environments. Do they support variable length subnet masks? RIP version 1, no. IGRP, no. Everything else, yes. What kind of resources are required on the router to run the protocols? As you can see, link state routers require a lot more resources, but that's because of the way that they construct their database, that link state database. Implementation, very, very simple for the legacy protocols, it can get extremely complex. Whoops. It can get extremely complex when you're dealing with link state routing protocols, even more so than EIGRP. We're going to be doing some implementations in this class. Our focus is going to be on the fundamentals, the foundation implementation strategies, but I will demonstrate some of the more complex components as we kind of move forward through the rest of our discussion. This you need to know for the exam, no doubt about that. You need to know what algorithms are run by which protocols. Distance vector, under there we have RIP, EIGRP. As you can see, RIP uses the Bellman-Ford algorithm. EIGRP uses dual. Dual stands for the diffuse update algorithm, or diffusing update algorithm. Link state, we use Dijkstra's algorithm, also referred to as the SPF algorithm, shortest path first. Dijkstra's algorithm wasn't specifically designed for OSPF or ISIS, but it was adapted for use with those protocols. As we go through the routing protocols individually, we're going to learn about what each of these algorithms do and how each of these algorithms work. We're going to actually spend quite a bit of time doing that. We also talked about the concept of metrics. A metric is a measurable value assigned by the routing protocol to differentiate the paths to a single destination. Oftentimes, we'll just simply call this path cost. I don't generally like to use the term cost because the specific metric name for OSPF is cost, but path cost is one of those values. And we've already talked quite a bit in detail about this concept of path cost and how that's associated to different algorithms. All right? So let's break down each of the protocols that we're going to be going through over the next few chapters, talk about some of the characteristics of these protocols. Your slides might be slightly different. We just recently updated this. So, all right? Talk about some of these differences. Let's see. Is there a way, we have a question from online, is there a way to determine the routing protocol from a host on the LAN outside of Wireshark? Actually, there really isn't. In other words, there's no real enumeration technique to identify the routing protocol that you're using. Now, it's not to say that you can't discover that through various methods, right? We know that routing protocols send information to specific addresses, specific multicast groups, and so on. So we could monitor for those transactions, but that would require obviously some tools that we would run to do that. There really isn't a way to specifically identify just from opening up a command line prompt what the routing protocols are. All right, RIP version 1, RIP version 2, RIP version next generation. As we discussed before, the metric that is used is hop count. Now, from a scalability standpoint, we can only go 15 hops away in RIP. That's not very scalable. If the destination I need to reach is more than 15 hops, then we can't use RIP. Now, you have to think about where RIP came from and when it was developed. In the 80s, 15 hops was not really something we concerned ourselves with too much because routing was a very minimal concept in network design. Mostly it was just bridging and maybe some switching. As we mentioned before, the update address here is all ones, but in RIP next generation and RIP v2, it's multicast. 224.0.0.9 or FFO2:9. As you can see, we support VLSM with RIP, newer versions of RIP and not with the older version of RIP, as well as classless routing. Route summarization, not possible with RIP version 1. Again, another failing in the efficiency of the protocol. Authentication. We don't get into the specifics of authentication in this class, but we can actually configure routers to authenticate each other prior to sending and receiving routing information. Well, actually not prior. It's actually a message authentication hash that's used, but nonetheless, authentication would be a good thing, especially with a dynamic protocol. Authentication is a very important thing. Every 30 seconds we send out updates. The administrative distance is 120, and RIP runs directly over UDP using port 520. All right, so we see these characteristics. What's the problem? What's the problem? Well, the problem is scalability. The problem is the metric. The metric is about the worst thing. Hop count as a metric, not good at all. Very, very limiting in pretty dynamic networks. If you have networks that only have a few links and all those links are the same speed, yeah, maybe not so bad. But we don't typically see that with modern networks. EIGRP. As we saw, IGRP, EIGRP, those are the before and the after. Both protocols actually had a pretty good metric. We use a composite metric, which consists of different variables, but the primary components are bandwidth and delay. When we get into the discussion of these protocols individually, we'll talk about the metrics in more detail. IGRP uses all ones address to disseminate routing information, whereas we use multicast with EIGRP and EIGRP for IPv6. 224.0.0.10 or FFO2:A. See, prior to the class here, you guys probably would have looked at that FFO2:A and said, okay, well, I don't know what that means, but now it makes perfect sense, right? FF is multicast, A is the group number. A happens to be 10 in hex, right? VLSM, authentication, classless routing, absolutely. The authentication method that we use in EIGRP is MD5, an MD5 hash. It's actually an HMAC type of authentication, like a challenge response type of authentication. Both protocols, actually this is a typo, updates here were not incremental and bounded. Let me see if I can actually fix that. I'm not sure if I can or not. Let me see if I can fix that. So updates were sent here every 90 seconds. All right. Messed up my whole screen here, but let me go ahead and get back into the slide here and fix everything. Every 90 seconds we send out updates in IGRP, so it did periodic updates, but with EIGRP we're using incremental updates. All right, incremental updates with EIGRP. Bounded updates means that we're also only sending out updates to the individuals. What happened to the projector up there? Hold on. All because I wanted to change something. Now we lost our projector. Hold on one second. Sorry about that. We had a little bit of a difficulty with our WebEx here. Yeah, the audio stopped when I was trying to edit my slide. So we had a question online, what does it mean incremental and bounded updates? Incremental means I only send out updates when there's a change. I only send out updates when there's a change on the network. A topology change, a change in the metric, whatever. Bounded means I only send those updates to who needs to see them. I don't just flood them out to everywhere. I send them to specific neighbors or specific destinations. You'll see that this is how OSPF works as well. RIP doesn't work that way, right? You go back to our RIP diagram here. We're sending out updates every 30 seconds, whereas any IGRP IGRP every 90 seconds. The other thing you'll notice is that both EIGRP and IGRP have, both EIGRP and IGRP have an administrative distance of, well, 90. That's not true either. Holy cow. This slide is just no good. So IGRP, I fixed the slide now. IGRP has an administrative distance of 100. EIGRP has an administrative distance of 90. All right? Also notice that EIGRP and IGRP, probably not IGRP, but EIGRP sits right on top of IP. There is no transport layer function for EIGRP. It rides directly on top of IP using protocol number 88. Now you guys know what it means to say protocol 88. We're talking about the protocol ID field in the IP header. EIGRP uses protocol 88. What about OSPF? OSPF, we have OSPF version 2 for IPv4, OSPF version 3 for IPv6. Both of these use cost as a metric, which is proportionate to bandwidth. We'll again learn more details about the metric as we get into the protocols individually. You'll also notice that they only use multicast 224.0.0.5 or 224.0.0.6. They both support VLSM. They both support classless interdomain routing. Actually, technically, it's not really a term we talk about with OSPF version 3 because there really isn't any such thing as classful or classless in IPv6. They both support summarization. They both support authentication. In OSPF version 2, which is for IPv4, we'll do plain text as well as MD5 authentication. In OSPF version 3, we use IPv6 extensions for our authentication process. The administrative distance is 110 for both, and OSPF runs directly on over IP protocol 89. That is both IPv6 and IPv4, protocol 89. You don't need to know that information, of course, for the exam, but it's useful if you're troubleshooting or if you're capturing information. We had a question earlier about how could I identify what type of routing protocol is being used. If I was to do a Wireshark capture and I saw a multicast packet come across my capture with protocol 89, I would know that that's OSPF. If I saw a Wireshark capture come across with protocol 88, I'd know that's EIGRP. What was the protocol for RIP? Technically, there was no protocol for RIP because what did RIP use? RIP used UDP. So actually, the protocol ID in the network layer field would have been protocol 17, which is the protocol for UDP. Protocol ID for UDP. So that concludes our introduction. All right. Now what we're going to do is we're going to obviously move on into doing the configurations of each of these protocols. All right. So we'll go ahead and end this recording, and then we'll get into the next lesson.